U of M, Michigan. And he'll be talking about databases and some things that he has been doing there on how to gather this data together. And this should be useful for us to think on a way if you want to share networks across the different groups. After that, we'll open the floor for discussions about any of the three talks, or basically any of the talks we had throughout the day. We have a shuttle at 5. So if we finish the session before 5, just mingle around talking, and a dinner at 6:30 at the bistro. Do we know how we get there? We just walk.
Yeah, I think there's like maps on the tape.
So there's a outside.
The hotel shuttle will take us there. Will take us anywhere we want to go. So if we just book it,
right?
It's like 6:15. They will drive us.
I imagine if it's a place that we have been around before, it's not far. We just walk to downtown, right? But yeah.
So what time should we meet to walk?
Meet to walk.
Good to walk together.
Yeah, the group dinner says 6:30, so maybe 6 o'clock in the hotel.
6 in the lobby.
6 in the lobby.
Sounds good.
Yeah, sounds good. So,
thank you. I'll be talking about databases, and I will warn you this talk is slightly technical, and the talk is mainly driven actually from a perspective within our group. So we kind of had this need of reorganizing how we manage our own data, and the way I organize this talk is the first part will primarily be a more theoretical and abstract way to think about this. And then the second part will be more specific about how we actually derive certain design principles and implementation principles to set up a new way to organize our data using a database system as. So motivate this, why scientists should even care about data science in general. Actually, the University of Michigan launched this $100 million heavy data science initiative a bunch of weeks ago, and it's one of the main resources for us to think about and actually get infrastructure for this kind of project. And another reason, of course, is we have these large sets of data and we have these large parameter sets, and I use this example of convex polyhedra, which were self-assembled into various structures, as the primary example throughout the whole talk, and that is because illustrative kind of problem that we try to attack here. So this is a work where 142 convex polyhedra were self-assembled, and through the means of calculating one of the main results from this work was actually to find relationships of certain order parameters. Coordination number in the dense fluid, so a number of first neighbors, polyhedra, these shapes. You can clearly see that there's some correlation between a high IQ value correlates with these kinds of structures, so FCC and BCC crystals, and on the other hand we have pneumatic crystals here for a low IQ value. Another nice correlation was the coordination number in the order phase and then the dense fluid, which is pretty apparent. The point that I want to make here is that and kind of structure assembled of whole is not that how to the vision that will kind of guide this whole talk is that as we produce data, we want to have it instantly available and searchable. And the first part here with available is usually a given. So, for example, within our group, we're usually storing all the data that we produce on a file system that is accessible by all the group members. And so it's usually already available, but searchable is kind of an issue. So if you want to look at other people's data or maybe even other groups' data, you usually need some kind of guidance that will help you to figure out what's where and actually find out maybe even what's available. So it's the two parts here that kind of drive this whole reorganization of putting data that may have been loosely structured in a file system in a more coherent way into some kind of database system. So just to move further, I lay out this simple model workflow here that we use, I guess. We usually start with a definition of a parameter space. So in this case, this was the range of densities that we look at, and then we'll produce this data. So in the Monte Carlo simulations to self-assemble all these structures, and then there will be the identification of the order parameters, and then the final step is analysis of the data. So essentially finding those correlations and plotting that. And I will say this difference between post-processing and analysis of data is kind of a gray area. I wouldn't say there's like a clear more data that, again, needs to be stored, while the analysis step where we these correlations. So if you follow all these steps, then we're done, right? So science paper, we publish, but of course not true. In reality, we'll find out after analysis that we need to redefine our parameter space, and then we will switch back and forth between production and post-processing, and then so on and so forth, and we start to wiggle around in this feedback loop. And it still works. In the end, we will probably find something and publish. I see a few problems with this. One of them is that all of these steps are because there's such a gray area between post-processing and production, for example. We knowledge about the specific data structure in this case, and it's very hard for somebody else, for example, to actually take over one of these steps or get an idea of what's going on. And it's inflexible in the sense that, for example, if we redefine our parameter space and we find out later that actually our naming scheme, for example, and just to keep it very simple, is just not appropriate for the new kind of parameter space that we chose. So I will just this and say, okay, we can change this if we have a database which basically our data and the way that we access it. That's the essential part here. We can just modify this slightly and say, okay, we still need to define our parameter space. We still switch them back and forth between production, and then we just insert and update that into one database. And then we have search and aggregate functions on this data and extract data and use that to enter this feedback loop again in post-processing and a new production of data. This for now. By inserting and updating, and this search aggregate mechanism is improved in that any kind of database system abstracts data storage and data insertion and extraction. And what you find, you can do all this without databases and come up with a very sophisticated way to handle all your and juggle all your files. But what you will eventually do is kind of converge towards your own handwritten implemented database system. So I introduced a bunch of terms. I just want to try to find an example of who is not familiar with this. For example, an aggregation example on this kind of data that I just presented here would be to calculate the average coordination number for all records that are grouped by and grouped by the self-assembled structure. So we would group all our by structure class. So in this case, the grouping is visualized with the color, and then average all the coordination numbers within one class, and in this way created a new view on our data. And we didn't need to reorganize that in any sense. We just can create such a query on our database and get that result immediately. So definition, aggregation is a function that collects, groups, and processes data from multiple records to generate or a new set of. And I also want to be very clear about what I mean when I talk about data. So usually we have some kind of data generation process, which for us is usually a simulation, but it might also be like a non-trivial analysis step or even experiments. And these data generation will generate a so-called record, which is in this kind of model the smallest entity of data that we can actually handle. And this record will consist, on the one hand, units or binding networks, etc., or just numerical arrays. So on the other hand, we have the so-called metadata, which helps us to understand what the data is even about. And one way to think about this is that only with metadata we can actually make any sense of our data. So I can just throw a bunch of numbers at you. If I don't tell you what this is, you don't have any idea what this might mean. And the metadata can be as abundant as you can imagine. So of course we need some kind of, for us we need some kind of idea of how the data was created, so what kind of parameters were used. Like software versions, hardware environment, authorship, that might be interested to keep with the actual data. So to keep this record an entity that is not separated. One way we realized this to make this an easy process, actually not long ago we implemented a metadata output for hoomd-blue, which is our in-house MD tool that we use for our simulations primarily, and it will dump out just basically. So it will try to dump out everything about the simulation. It will dump file names that are produced and frequencies that data, and also about the context. So what time was it when software version did we use? What was the username of the output, like the process? So I want to say here is like attached to your file. It's possible, but it's so when I started thinking about this, how could we store our data and how could we handle our data within a database, one of the things that came to my mind, this is kind of anecdotal here, is we need to think about the format. We need some kind of format to put this data into our database. And then actually I realized that format, and this was illustrated here by the great Randall Munro. He says, to develop one universal standard that covers everyone's use cases, and then after that situation, there are 15 competing standards. And I'm pretty sure the same thing would happen for us. We have in this environment of different formats within our group, and that is just because the tools all produce very specific formats for the data that they care about. And we don't try to funnel everything into one universal standard that kind of covers every use case. But what we do is we care, so we don't care about formats, but we do care about the data. So just to illustrate this, we might have data in different formats. So this is a protein which we just pulled from the protein database. So it's in the PDB format, for example. And then we have the structure data that I showed earlier, which might be in our in-house POS format. And then this is just a polymer, which might be just a string or an array of XYZ coordinates. So all we care about is actually, for certain methods, is just the coordinates, for example. So we just pull out, extract this array of XYZ data, and once we have that, which is essentially an n times 3 matrix, we're good. And this is what we're interested in. So keeping all of this in mind, we kind of derive these design principles. We want to, on the one hand, we want to store raw data, because storing raw data has the advantage that we don't lose any data when we're trying to translate it into some other format. It allows for individual post-processing. It increases transparency. And this is actually quite crucial. It lowers the barrier for sharing. If I require of you to put whatever you do into some kind of format, that might just be too high of an energy barrier to actually do it. And then because we do this, because we store raw data, we want to have an on-the-fly processing. Because we put all of this raw data, which in the end is like a binary blob, into a database, it kind of becomes a black box. So we can still look at the metadata, but we cannot operate, so for example, do our aggregation functions or search within this black box. So we want to be able to collect and process the raw data while ideally this process is cached. So we can imagine if we operate on our data with very expensive methods, we do this trying to do our analysis. Operation takes a bunch of minutes or hours. So with this, I will ideas that were floating within our group, and try to implement which the implementation. So I will start with an example. We can imagine if we put all of this raw data from our first, all these into our database, and we now want to search for a set of trajectories with a certain number of facets x, and this might be clearly defined. This might even be. Then we want to look at only data with packing fraction greater than y, and some kind of arbitrary order parameters less than z. Traditionally, if we just had some kind of standard database, we could fetch these facets x, and then we get a result vector with all of these raw data blobs. But now the actual work begins. So we need to figure out what kind of formats are there in. We need to translate those formats so that we can apply our methods, and we calculate the packing fraction, and then select only those that are matching our criterion. And then we do a second method, and all of this becomes pretty cumbersome to actually we want it, and this is what we need to do for that. So we basically streamlined this process by saying all this translation of formats and application of methods should be automatically happening. So we put this, move this from the user space basically into our implementation, and said translation of formats and application of methods should be something that the computer actually can do for us. And what this essentially does is we have our database record, which essentially consists of the metadata and the raw data, just as I introduced in the beginning, and kind of pretend that we have a database record which consists of the metadata and the raw data, but also the results of our methods that we are looking for. So in this case, a packing fraction and some kind of other order parameter. And the way it's implemented is we still have an underlying database which cannot handle our raw data. We can fetch our records just as I showed before. And then I'm very happy that I have this network in here for this workshop. We apply a conversion using a formats network, which I will describe in more detail in the next slide. And once we translate it into formats that we understand, we can apply our methods, cache them, then select our result record and get the result immediately. So this format networks actually proved to be quite important for this whole. It allows to handle all these different formats, and I will show you how this works. Just giving a very simple example. We can strings and bytes. If we had a value of 42.0, for example, we can immediately say, okay, that should be convertible into an integer value, or into a Boolean if you use the convention that everything but 0 is true. And we can also convert this into a string value, which consists then of the characters 4 and 2, which is presented by this byte value. So this is, I think, intuitive. All we need to use this is we have our formats as the nodes, and we need some kind of adapters implemented that translate between those nodes. And if we had a different value, for example, we see the limitations of 42.1 cannot be converted into an integer value anymore. So it's intuitively not reachable. And then again, just to reiterate, if we have a name, we lose this whole part of our network. So this is actually part of the formats network that we implemented, because those basic types should be in there anyways. But to bring a more realistic example of the data that we care about, I mentioned that we have this POS file format, which is just really a non-standardized way that we store our data. We have our XML output from the hoomd-blue code, and I was interested in getting the polyhedral vertices, so I just implemented a very simple method that extracts those polyhedral vertices from our POS format, and then eventually I needed other things that got a little cumbersome, so I set up this intermediate format, which now is able to give me all these other values. And third-party format, if we add an adapter that is able to translate between this and the XML format, all the methods that operate on these kinds of formats are now also available for this third-party. So it basically boils someone just writing this one adapter to make this whole more accessible. And by having network, the way that we think about implementing methods changes slightly. So we first define our input format and then provide the adapters, and then in the last step we implement our method. So we can imagine that we want to calculate the packing fraction. And for this, we need the volume of our simulation box and the average particle volume and maybe the number of particles. So we just need some kind of adapter that extracts all of these values from the formats that we're interested in, and then we can calculate that value. And just to make this a little more hands-on, so this is an example. MongoDB is our backend server. We can use any kind of tool that handles MongoDB, and I'm showing this example with a tool that is able to display the data. So we can, just as an example, there's one record in here where we have data from our polyhedra zoo. This is what we call the whole pie chart, basically, that we can search for and aggregate. And there's also like the raw data. So here it says file type, POS trajectory file. So this helps the overlaying framework basically to translate between the different data plots, because it knows, okay, I know this format and I have these adapters available, so I can translate that into something that we need. And I should probably zoomed up earlier. It's just the same thing. And usually, so these GUIs are important if you're working with databases, because otherwise you're basically shooting in the dark. You want to be able to visualize that, because you need to visualize the data and the way it's structured and be able to formulate your queries and aggregation operations. But because we are a computational group that is usually using Python, I just want to show here just a different way to access this data. If we're producing thousands and thousands of data blobs, we don't want to put them manually into our database, but we be able. It's just another way to access this. I just want to show here one example. The example that I showed earlier would be implemented as this very simple query. So I just say facets 20, and then I can use these different defined methods to query for certain values. And this means the underlying system will actually fetch the data and then apply those methods. That is the point here. This is a semi-live demonstration that I recorded earlier. I just want to show here that I can actually use this to, I'm not sure I start this here. Okay, now it's going. So I actually formulate the base, and it then refetches all these records, applies the method, and I can immediately plot that. And using a very crude method and query here, I can actually reproduce these relationship that I was showing earlier. So I will just skip ahead to the finish line here. So yeah, I just want to say that it's very easy to create these kinds of plots once you have all your data organized within a database. And I just want to thank Ben Swertlow, who's another grad student in our group, who helped me to provide these examples. The storage and data handling, this is the main point, I guess. And by storing raw data, we ensure compatibility. And we can use a network of formats and adapters to increase compatibility and to make sure that methods that we implemented and defined once are reusable for basically the whole data that is interesting to us. And we're also definitely looking for beta tests, whoever's interested in this too. Thank you.
Time for questions or something. Or comments. David, how is that different or compared to like the types of things you guys had in the Cambridge database?
When people send me stuff to deposit, it's very often a tar file full of results with XYZ coordinates and energies. And I just store the tar file, or I put in a link.
You don't even open, you just
Yeah,
take the tar
exactly.
file.
So that everybody who wants it can just download the tar file.
Mm-hmm.
There's not much point in me trying to process it. But I invite people to make web pages that match ours if they want to. So most of our stuff has, for each potential, a web page with a table with the energies, the coordinates, and pictures, perhaps animated GIFs, where you can click on XYZ and it will take you to the XYZ file.